Hello, and welcome to Empowered Learning. This video will be an application of evaluating definite integrals, and specifically we're going to talk about the difference in between displacement versus distance. So the first thing that we need to do is to find what displacement means and then figure out how distance differs to that. So displacement is just the net change in position of an object, which is also in terms of the area under the curve of a function. Is the net area under the curve of some function f of x. Now displacement, we define that as an infinite sum of areas, or we can put it another way as a definite integral, as the definite integral from time t1, which is the start time, to t2, the finish time, of the velocity of some function with respect to time. And of course, if we take the antiderivative of velocity, that will be position, which is a function s of t. And we look at that from s of t sub 2 minus s of t sub 1. So we could look at it this way, but really the way that we should look at it is kind of like this. S of t sub 2 minus s of t sub 1. Okay. So let's note here that displacement takes into account for negative movement. That means moving backwards as well as positive movement. So to kind of give you an example here, let's say I have some number line here, and this is 0. And so let's say I start here at 0. Let's say I move 3 units to the left, and then I turn around from here and move 5 units to the right. So as far as displacement is concerned, I am right here. Okay, I've moved 3 units to the left, and then I've moved 2 units to the right. So the net change is going to be going 3 in one direction plus going 5 in this direction. So displacement wise, the net in position I've changed in whatever units I'm talking about is 2. However, if I'm talking about distance, as you see, distance is the total ground covered. And so we know that distance can never be negative. So if I started here again and I moved 3 units to the left, then that means I went a distance of 3 whatever units. And then if I turn around and go another 5 units back in the other way, that means I've added another 5 units to that. So I've went a total of 8 units in that case. So that is the difference in between displacement and distance. Simply put, our displacement here is we went a net 2 units, but the distance here would be I went 3 units in one direction, 5 in another, and so the total distance I traveled is 8 units. Okay? So that is why here I say distance is total ground covered regardless of direction. And we need to recall that distance can't be negative, and also recall that in mathematics the way we express distance is with absolute value of a function. By definition, the absolute value operation or function forces its result to be non-negative. Okay, and so that's why we use absolute value in that way. And therefore, we could say that distance is actually the absolute value of displacement. Okay, so looking at it in terms of a definite integral, if we were to try to find the distance of some velocity function, we would have to do the absolute value. And really what this entails is, if we have a function to where a part of it has an area that is under the x-axis, we will have to account for that by doing the negative of it to, in turn, make that positive now. And so we'll be flipping an area from from being under the x-axis to above whenever we talk about distance. However, when we talk about displacement, we can leave the area as being negative, and we're okay with that. All right, so let's look at this problem to sort of get an idea of the difference in between displacement and distance. So we have some particle, and they're moving along a line so that its velocity and time can be characterized by this linear function. And of course, our units is in meters per second. We want to find the displacement of the particle during the time period from 1 to 4 seconds. Okay? So from what we learned, first off, we know that if we're going to find displacement, let's write that again here. Let's get rid of that. Displacement is just going to be, in this case here, this is going to be my T1 and that's going to be my T2 from 1 to 4 of just this function here, which is our velocity function with respect to time times dt. Of course, this 5t minus 12 is our velocity function. So here all we have to do is just integrate this and figure out what it's going to be. Not too hard. And of course I'm going to just say that all this is just equal to d to make it more simple. So here if we integrate that, then that's going to be 5t squared over 2 minus 12t, and all that will be evaluated from 1 to 4. Of course, first we'll plug in 4 to our function, minus 12, 4. And then we'll do the same thing with 1. Okay. So now from here, we know that 4 squared is 16. And 16 divided by 2 is 8, and 8 times 5 is 40. So we know for that very first term there, we have 40 minus 12 times 4 is 48. And then here we know that we have minus, so if we go ahead and distribute, we have a minus 5 over 2, since 1 squared is 1. And then 1 times 5 is 5. 5 divided by 2 is 5 over 2. And then here we have 12 times 1 is 12. And since we have the subtraction sign here and a negative there, negative times negative is a positive. And of course from there, 40 minus 48 is a negative 8. And negative 8 plus 12 is a positive 4. And then that would be minus 5 over 2, which in decimal form is just 2.5. And so the difference in between that would be 1.5. And of course this would be meters. So what we're saying in this case for displacement is that the net change in position from time t equals 1 to time t equals 4 was just 1.5 meters. So we could have went back and forth all day long. At the end of the day, after going all that back and forth, the net change in position from when we started is only 1.5 meters. Okay? So now let's talk about the actual distance traveled. And of course, distance is different. To figure out the distance, we would actually have to go from 1 to 4 and look at the absolute value of 5t minus 12 dt. And I'm going to pause for a second and actually draw a graph of 5t minus 12 so that we can see what it looks like, as well as sort of depict how we're going to break up this definite integral so that we can evaluate it properly. Okay, so here is a graph of what 5t minus 12 looks like. So it's this line that's right here. And if you see, since we're looking at this particular function, in particular the area under the curve of this function from time t equals 1 to time e equals 4, we see when we start here at 1, from 1 until about 12 fifths, we have area that's under the x-axis. And then from 12 fifths on the 4, we have, on to 4, we have area above the x-axis. The reason that we know that 12 fifths is where this switch happens from being area under to being area above the x-axis is because that's where the x-intercept is. Simply put, if we just set this equal to 0 and solve for t, we'll see that t is 12 fifths. So that's something that we have to know. So looking at this, if we're wanting to figure out what the distance of this function will be, and actually I should be calling this v of t, not f of t. So let's try to get rid of that. So here, if we're trying to find out the distance that is traveled, we have to take this area and look at it in a positive manner. So this will be the negative of 1 to 12 fifths of 5t minus 12. And of course that would be dt. And then plus from 12 fifths to 4 of 5t minus 12 dt. And of course here with this negative here, we could really look at this from 1 to 12 fifths of 12 minus 5t, like that. And of course, everything else here we can keep the same. All right, so this is how we can look at this. Now notice that since we know that we have a line here and these areas that are represented here are actually right triangles, we really could figure this out just by adding these two areas together here. And so I'll go ahead and do that, but then afterwards we'll see how we can actually do this by taking any derivative as well. Okay? So we'll call this first area here A1, and we'll call the second area here A2. So for that, for area A1, we see that the base of the triangle is the difference in between 1 and 12 fifths. And of course, 12 fifths, if you look at that as a decimal number, is just 2.4. So the difference in between 1 and 2.4 is just 1.4, okay? So area 1 is just going to be 1/2 times the base, which we'll just say is 1.4, times the height, which in this case goes from here down to there, which is a difference of 7. Okay? And so now if we have 1.4 times 7 times 1/2, we end up getting 4.9, and in this case, this is going to be meters. Okay? If we do area A2, this would be 1/2 times the base, and so this base here is a difference in between 4 and 12 fifths, which is 2.4 again, which is just 1.6. Times the height, and this time we see that when t is 4 for this function, and so just in case you didn't realize what that was, that's actually a t. Here we know if we plug in 4 here, 5 times 4 is 20, 20 minus 12 is 8. So that height would be from here to there, that would be 8. And so of course if we have 1/2 times 8 times 1.6 there. So half times, let me make sure I do this again. Half times 1.6 times 8, that will give us 6.4. And of course, that will be meters. Now, of course, for here, if we add these up, we'll see that this actually ends up giving us, so that's 3 carry 1, 11.3 meters. So the actual distance that's traveled, even though we've been going back and forth all this time, is essentially 11.3 meters. And that makes sense because the actual distance traveled in one direction is different than the other. And of course, there was some kind of net change, but in all that movement, we still went a total of 11.3 meters. And so now what I'll do is switch back to what we were looking at before and solve this via the antiderivative way. All right, so now we're back here, and so if we're going to write this out, of course, we need to have this looking like 1 to 12 fifths of 12 minus 5t, and we know why we said that, plus 12 fifths to 4 of 5t minus 12, all that dt. And so from that point, we just need to integrate both definite integrals and evaluate it over its limits of integration. So we'll come over here and now do them. So for this first one here, it is not working well with me. So we have that. And so now when we integrate, that will just be 12t for the first term. And this will be 5t squared over 2. Because of course we add 1 to the exponent and then divide by that. And of course this will be from 1 to 12 fifths. Of course for the first term this will be 12 times 12 over 5 minus 5 times 12 over 5 quantity squared all over 2. That is for the first term. And of course minus. And then we'll do the same thing here, but just plug in 1s. So if we do that, that'll be 12 times 1 is 12. Minus 1 squared is just 1. So that'll just end up being 5 over 2. And just look at it like that. Okay. And so now from here, if we keep on going, we'll see that we have 144 over 5 minus, and of course this 12 over 5 squared is just 144 over 25. And if we multiply that times 5, have it divided by 2, that just reduces to 5. And really what we have is 1/2. And we're going to write it this way to make the math easier. 1/2 of 144 divided by 5. Okay. So of course, here we have a minus 12 and a plus 5 over 2, which ends up giving us half of 144 over 5 minus, and of course 5 halves is just 2.5, and so if we do a negative 12 plus a 2.5, that'll give us a negative 9.5. And of course, from there, if we go ahead and calculate that, see that'll give 144 divided by 5 times 0.5, and then minus 9.5, that will give us 4.9. Of course, that's meters. So that's for this first piece. Now, for the second piece, we need to do the integral 12/5 to 4 of 5t minus 12 dt. Of course, if we do that, then of course, this is 5t squared over 2 minus 12t, and we're evaluating that from 12/5 to 4. And just like how we did last time, we'll plug in 12 over 5 squared, divide that by 2, minus 12, and that would be 12 over 5 there. And that's for the first one. For the second one, sorry, messed that up. I should be plugging in 4 here to begin with instead of 12 over 5. So let me go ahead and fix that. Okay, so I went ahead and I fixed that. So this is what it should look like. And of course, if we move down and continue on, we know that 4 squared is 16. 16 divided by 2 is 8. And 8 times 5 is 40. So we have 40 for our first term there. Let's get that 0 looking a little better. Minus 12 times 4 is 48. And then for all of this, just kind of like how we had up here, we saw that this particular term looks the same as that one. So we're going to end up with a minus 1/2 times 144 over 5. And 144 over 5 doesn't look too hot. So we'll fix that. Okay. And then this will be plus now, since we can distribute. This will be 144 divided by 5. Of course, 40 minus 48 is a negative 8. And that will be plus 1/2 of 144 divided by 5. And again, if we do 144 divided by 5, that'll be 28.8 times half of that. Will give us 14.4. And 14.4 minus 8 will give us 6.4. So that is what that would be. And of course, if we added both of these two answers together here, that would end up giving us the 11.3 that we need. Okay. So of course, our total here would be 11.3 meters. So although the displacement is only 1.5 meters here, the actual total distance that we traveled with that particle is 11.3 meters. So therefore, to write this properly, we would just say the distance, which is from 1 to 4 of absolute value of, make sure absolute value is pronounced like that, would just be sum of 4.9 plus 6.4. And of course, that'll be 11.3 meters.